Okay, we're happy to have Nicolas Guès telling us about a homotopy-theoretic approach to representation stability.
Thank you, Jeremy, for inviting me here. So today I'll explain uh, some things I worked on about representation stability. So first of all, I want to talk about classical homological stability. So I'll say that the phenomenon of homological stability is kind of there's a meta theorem that says that for many families of groups or spaces that come in families indexed by the integers, so I have a family of groups or spaces. It happens that if one tries to compute the homology with coefficients, let's say in Z to start with, there's often a transition map, a stabilization map that goes from Gn to Gn plus 1 that induces a mapping homology. And this happens to be an ISO if the homological degree is sufficiently low compared to n. So let's say this is an ISO if n is sufficiently big. And this is something that happens a lot. So let's give some examples. So we can take G to be the symmetry group. This was proved by Nakaoka in the 60s. Actually, he even computed the entire cohomology ring. This works for GLN of a field. This was done by Quillen. It works also for many rings, satisfying some condition. This was, I think, in the 70s, if I'm not mistaken. For braid groups, also this works by Arnold. And there are many more examples. For example, the mapping class groups of surfaces. Of genus G, and I make the genus G go to infinity. So this is the stabilization map is induced by including a surface with one boundary component into another with one genus higher, let's say so, like this. Okay, so something that will be the core of this talk today will be a family of spaces that are the configuration spaces of manifolds. So fix a manifold. So we will fix a topological manifold, M, which is of dimension, let's say, so far of dimension D greater than 2. And I define the configuration space on endpoints of M to be the space of n tuples of points in M that are pairwise distinct. So xi is different than xj if I is different from j. And there's so this is called the ordered configuration space because each of these points has a label in one n, and I can make the symmetry group act on this and obtain the unordered configuration space where a quotient by Fn. So this is also the homotopy quotient because the action is free. And alternatively, this will be useful to see this is the same thing as the embeddings, the space of embeddings from a finite set on n endpoints inside M. And something that was proved a long time ago by Joseph McDuff and many other people. So I think for manifolds, an For open manifold, it was by Magdoff. I think it was in the 70s. So if you have an open manifold, so if M is open, you can find the stabilization map from the configuration space, the unordered version, and you can just add a point on the boundary and push it inside M. So this is, let's say M is something like this. If I have 3 points, I can just choose a colored neighborhood at the boundary and add a point inside. So there's a well-defined stabilization map, and she proved that this induces an isomorphism in HI on the configurations. Plus one is an ISO in a range growing with N. So this kind of theorem is interesting because the homology of these groups of spaces is notoriously hard to compute. And if you know that there's a homological stability, you can either hope to compute more groups. For example, if you know that HI of configuration and endpoints is isomorphic to the one to n plus 1 points, you can identify this with the homology of some limit space that I will write conf infinity of M. And maybe this has more structure than just the configuration on endpoints. And so you can maybe extract some information from this fact and help compute this part. So another, let's say, an orthogonal thing people think about is understanding the stable homology, so the homology of the colimits of these spaces. But today I will mainly try to prove the homological stability theorems or related things. So this is the kind of theorem we're interested in, but sometimes there are a lot of situations where it doesn't work for kind of obvious reasons. So for example, what happens if I look at the ordered version? I'm sorry, so this was the unordered configuration space. Let's try to compute some example. If I look at configurations ordered inside R2, this is a classifying space for the pure braid group on n strands. And it's quite easy to see when you look at the presentation of the pure braid group that the H1 of this, being the abelianization of this, is a free abelian group on n choose 2 generators. So there is no hope for it to stabilize, simply because the rank of the group grows polynomially. But it's still interesting to notice that you have some polynomial growth here, and maybe there's still something to say because in this time the configuration space on n strand on endpoints is not only a space, but it's a space endowed with an action of the symmetry group. So this inherits an SN action, and maybe the good thing the good way to think about this family of spaces, the ordered ones, is not as a collection of spaces, but as a collection of spaces endowed with an action of the symmetry group. And this is what was done. This is the idea of representation stability. So in in the 2010s. And this was founded in a paper by Church and Farb, and also developed a lot by Church, Farb, and Ellenberg. So they noticed a phenomenon happening for families of representation of the symmetric group that arise naturally in the wild. So I need to define something. So we'll say that a sequence Vn of Q vector spaces with Vn being a representation of the symmetric group Sn is a consistent sequence if you have stabilization maps from Vn to Vn plus 1 that are equivalent with respect to the inclusion of the symmetric group Sn inside Sn plus 1. So I'll say it with this diagram. So covariance condition. And a typical example that we will be following through all this talk is typically in the configuration spaces. So if I take Vn to be the dth homology of configuration spaces of n, but we'll come back to this later, and I can look at homology with rational coefficients. And as Vn is a rational representation of Sn, you can ask what is its decomposition into irreducible, because we know that irreducible representations of Sn are classified. Representations of Sn. These are classified by Young diagrams. So partitions of n. And so I can write that the n is the sum of Cn, I can say that it's a sum for every W in the irreducible representations of Sn of W to a certain power. So maybe I'll change my notation. So write this. So V lambda is a partition, and V lambda is the representation corresponding to it. And I can write that the n is sum of V lambda to the C lambda, which is the multiplicity. And now you can, so how to make sense of some notion of stabilization in this case, because we have representations of different groups. So we need to know how, if you want some stabilization phenomenon, we want to relate different representations of different groups. So that's what we're going to say here. So if lambda is a partition of an integer, an integer m, so I can represent it as a Young diagram like this. So here I have 10. This is a partition of 10. And I can call V lambda of n for each. So maybe for any n greater than m, I will write V lambda n, the representation corresponding So not to lambda, because lambda is a partition of M and not of M, but I can simply take this Young diagram and add a bunch of boxes on the top line until I get a partition of N. So with a single partition lambda, I can define representations of any symmetry group. And the phenomenon that was noticed for many families of representations is the following. So theorem. So let's say I want to state it slightly sloppily. So yeah, let's say it's a meta theorem as before, because it applies to a lot of things. For many sequences, Vn of consistent representations of the symmetry groups, if you decompose Vn as a sum of V lambda n with multiplicities C lambda n, so lambda is a partition of any integer smaller than n. You can observe that C lambda n is independent. This is independent of n for n big. This is the phenomenon of multiplicity stability. So that's what was called multiplicity stability. Any questions so far? Okay. So a question. So in particular, this holds for configuration spaces of manifolds, of closed also manifolds. And this is striking because for unordered configurations, you cannot expect to have homological stability if you take a closed manifold. For closed manifolds, and this was done by Church in 2011, I think. So a natural question is how you can get this kind of stabilization theorem. How to know when this happens. And so Church and Farben Ellenberg happened to find a very nice characterization of this, which is very combinatorial and reduces the study of all these multiplicities to the finite generation of a single object, which I'm going to introduce now. So I'll call Fi the category of finite sets and injections. And an Fi module would be the category of, so Fi mod would be the category of Fi modules, which are simply functors from Fi to the category of abelian groups. Or so, and maybe I'll write FEQ, Fi mod Q, if I want to go to rational vector spaces. And one thing to notice is that any Fi module V gives a consistent sequence of representations, gives a consistent sequence of representations of the symmetry group. So if your FI module is with values in abelian groups, maybe you can tensor it with Q to get something that's tractable in terms of multiplicities. But the interesting thing is that we can show a bunch of things about integral FI modules, which is a bit more general than what I said earlier. So this gives a consistent sequence of representations. And you can see that in particular our configuration spaces can be seen as a functor from the opposites of the category Fi to spaces by sending a finite set S to the embeddings of S into M. And you can see that this is contravariant, and including injections just induce the maps that forgets the point or the level of the configurations. This is conf S of M. Okay. So why did I define this category of FI modules? So the interesting point is that I can say that so an interesting thing will be to understand if I can read the multiplicity stability phenomenon at the level of the FI module. Like this is an algebraic object. What can I say about it that guarantees me to have this stabilization phenomenon here? And this is what I'm going to say now. So I say that an FI module V is said to be finitely generated if there exists a finite set W inside all the VNs such that no proper sub FI module of V contains W. So roughly this says that every point in V is generated by W. So it's really saying that these is generated by W, contains W. Okay, and a theorem, this time it's a real theorem by, I think it was Churchill, Berger, and Farb. And you can show that if V is a finitely generated FI module, then it satisfies multiplicity stability. So maybe I need to add that to multiplicity stability. For multiplicity stability to have a meaning, you need to be over Q. But this is interesting because, and I actually think that it's an equivalence, if I'm not mistaken. But in any case, you reduce this whole counting multiplicities thing to a property of a single algebraic object. V will be an FI module, and it suffices to find a finite set of generators to prove multiplicity stability. So now I'll state the kind of things I'm going to prove. So the thing I'm interested in is not in the cohomology groups of configuration spaces, but rather in homotopy groups. So my result is that if you take M, which is a topological manifold of dimension D greater than 3, then you can look at the homotopy groups by P of the configurations. So sadly, as this is a contravariant functor on FI up, the homotopy groups will be also a contravariant functor. So if I want to use representation stability, I want to dualize and take the home with Z or the X with Z. So also, I didn't mention the fact that you need to find a base point for the homotopy groups to be well defined, and that's a little inconvenience, but still, this thing would be, you can have a structure of an Fi module if M is of dimension greater than 3. And I can look at these two groups, which would be Fi modules, and the theorem is that, so the first one is generated in degree less than 2 ceiling function of p minus 1 over d minus 2 plus 1. And it is presented, so I didn't say what was the meaning of an Fi module to be presented in degree something, but it's equivalent to saying that it is the quotient of an Fi module generated in degree. Sorry, so something is present in finite degree if it's the quotient of a finitely generated Fi module by another finitely generated Fi module, and the degree will be the same. So this is presented in degree more or less the same. There's a slightly larger bound, and we have exactly the same bounds for the X groups. So this generalizes, so this completes a paper of Jeremy and Sander Cooper's. So as a paper from 2016, which stated that these were finitely generated, but without a bound, and they gave an explicit bound over Q. So far I talked about representation stability, and the name of my talk was a homotopy-theoretic approach to representation stability, and there's not much homotopy theory here for now, so now I'm starting to maybe to explain why we're doing a homotopy-theoretic approach to prove this. So the idea is the following. We saw that if you hit this family of spaces with either cohomology or homotopy groups, maybe I need to dualize here, so home to C or X, you always get finitely generated Fi modules. So a natural question, and I think it was asked by Steven Sam when noticing this phenomenon, is can we formulate the finite generation property directly at the space level? Can we see the representation stability phenomenon directly at the space level? And the idea will be, maybe it's easier to prove it at the space level, and then I can from some theorem that can bound the generation degrees of these, deduce a stability for this kind of invariance or cohomology theory and homotopy groups. And so another question is, if I can have a notion of finite generation for the space and finite generation for its invariance, and how can I relate the notions of stability? let's tackle the first question. How can we see? How can we define a representation stable space or homotopy type? So for this, I will use a little tool that's called FI homology. Okay. So this is simply so if I take an FI module, I can construct the functor that takes this FI module and construct an FB module. So FB is the category of finite sets and bijections. So I just forget all the non-bijective injections. And I send an integer n to V of n, but I mode out by all the images of V of s. Sorry, maybe let's stay coordinate free. So I'll take a finite set T, and I send it to V of T, moded out by all the images of its subsets of. So you can see that saying that it's easy to convince yourself that an FI module is generated by classes in finite degrees if and only if this functor is eventually zero. So because this will mean that D of T is exactly covered by all the images of the smaller things. And I call this functor H0. And you can left derive this. To define the ith group of FI homology. And this captures a lot of interesting things about an FI module. So in particular, H0V is eventually zero. So I will write it like this. If and only if V is generated in finite degrees, and H1V and H0V. So if I have more, if I add the condition that H1 of V is eventually zero, this is equivalent to saying that V is presented in finite degrees. And the moral of this story is that I can prove I can prove representation stability for V by computing these HI groups, these FI homology groups that will, in a sense, give quantitative bounds on the stability properties. And what's interesting is that this FI homology H can be generalized to spaces. So let's see how we can do that to FI spaces. So you'll notice that in my case, configuration spaces are FI op spaces. So we'll need to adapt this if I want really to prove things. But let's say as an example, I will look at FI spaces. So the observation is that H0 is the left adjoint. So the classical H0, which is a functor from FI mode to FB mode. This measures, in some sense, the generation property of V. It is the left adjoint of something that goes the other way around, and this is the extension by zero functor. So I can take D, which is just a bunch of representation of the symmetric group that have no coherences whatsoever between themselves, and send it to the same, and any non-bijective map is sent to zero. And I'll call this alpha. And now you can see that if I look, so let's define FI spaces No. So I'll call S. Maybe I don't need pointed spaces. So S is the category, the infinity category of spaces. And I'll call FIS the category of functors from Fi to spaces. Same thing for FB. You can define some Fi homology functor from this, and you can define it as the derived left adjoint of the extension by the extension by zero functor. Okay. So far I just defined something. It's rather abstract, and we're not convinced that it has any application. So first question is, can I describe this H of X if X is an Fi space? If I want to prove. So essentially, you see that for Fi modules, you want to prove that H0 of V is 0 and H1 of V is 0. And actually, by a theorem of Church and Ellenberg, this implies that Hi of V is eventually 0 also. And the correct analog for a space will be asking when this H of X, so maybe I need to recall that. So Hi of V, I can see this as the ith homology group of the total left derived functor. So I have a map H from Fi complexes to FB complexes, which will be the total derived functor of this functor H0 here. And so essentially what I want to prove is that these HIs are 0. So this amounts to say that big H of V, if I evaluate it on a big N, this will be highly connected because its first homology groups will be 0. So the goal here is to ask when Hx for a space is highly connected. This is the correct analog. Well, at least I didn't argue why it's correct, but at least it's the natural question that we can ask when this is highly connected. And so most importantly, if I know that Hx is highly connected, so this would be some sort of space level representation stability. Can I deduce that this is the case for its invariant? So can I deduce that H of, let's say, the cohomology of X, so no, as I have an Fi space, I will take the homology of homotopy groups of X to be highly connected. And by what I said earlier, this implies representation stability in the sense that these groups will be presented in finite degrees. Okay, so I'm going to answer these questions and finally explain how we can prove this theorem about homotopy groups. So the first theorem is that there's a very nice description of Hx of n. So if I take X, which is an Fi space, Hx of n it is the homotopy cofiber of the natural map from let's say that instead of, so I evaluate this on finite set. So I will evaluate this on something I will call underline n, which is simply 1n finite set. And you can prove that this hx of n is the colimit over all the strict subsets of n of x of s. This maps into x of n. And you take the homotopy cofiber of this. This is called the total cofiber. And that I will write, so maybe I'll write this completely. Total cofiber of this diagram indexed by subsets of n. And which to S maps is an S to X of S. Okay, and this is something rather common in homotopy theory. And this kind of total homotopy cofibers appears a lot in functor calculus. So the hope is to link these kind of questions to functor calculus somehow. So this is the first thing, description of Hx. So the second thing is that I can relate. So maybe I need a small definition. How many time do I have left? Okay, so recall that what we want to do is for an Fi module V to control if H0 of V and H1 of V is eventually 0. And what I want to control is, I want really a quantitative result. So I'll define the generation degree of V, T0. So there are many ways to define it, but I'll say that it's the maximum n such that H0 V of n is non-zero. Yes, it's non-zero. So this controls what's the maximum degree, maximum cardinality of generators of V. And I can define similarly T1, which will be the max n such that H1 of V of n is non-zero. And my goal is to bound these two quantities. And I can do the same thing for a space. So I can take T0 of a space X, which would be the max n such that, so this time Hx is a space, but I can look at it by 0. So as soon as pi 0 is not connected, is not a point, and same for, yes. And similarly, I could look at Tn of x, which would be the max n such that Tn of hx and 0. So these are the analogs for spaces. In particular, if I know that this total homotopy cofiber is highly connected, I will get that T0x, T1x are small. So the question was, if I know how to control these, how can I control these when V is some algebraic invariant of X, like homology or homotopy groups? And this is the following theorem. So let's take, so okay, so I'll say two different things. So take X, which is an Fi space. And then I can relate these two groups, these two bounds with the following thing. If I look at the homology of X, HP of X, I can ask whether this is finitely presented as an FI module, and you can show that T0 of HP of X will be controlled by, so it's 2 TP of X plus 1, and T1 of HP of X, I think it's 2 TP of X plus 2. And there's a variant for co-FI spaces. So functors from FI up, the opposite category, to spaces. In particular, this applies to configuration spaces. And the result is the following. So for homology groups, I have the rather intricate bound that depends on, so I'll call this f of p. So this function is bounded, it depends on all the tks of x for k smaller than p. And this involves some combinatorics of partitions. And I'll explain later why we have this strange bound. So I have the same thing for the cohomology for the T1. Maybe there's a +2 here. And this time the simple thing is for homotopy groups. So maybe as I need to have a well-defined homotopy groups, maybe let's say that X is a pointed FI up space, which in this case, it's a bit harder to make this work for configuration spaces because you have no canonical choice of base point, but let's put that under the carpet for now. And I can look at the dual of the homotopy groups of X into Z, and this will be also controlled by 2TP of X plus 1, and I'll have the same thing for the X. I'm sorry, I'll have the same thing for T1 and also the same thing for the X groups. So so what does this tell us? It says that if you can control these total cofiber, so in the case I wrote this, X was an FI space, so we have a total cofiber. If X is a FI up space, we need to dualize this theorem, and you can show that this time H X of n. So maybe I'll write it in here. So if X is an FI up space, Hx of n will be this time the total fiber of the cube that sends a finite set S, finite subset of n to X of S. Okay. So now I know that I can prove representation stability theorems about invariance by showing that some total fibers are highly connected. So I'll write this here. So now we know that highly connectedness of total fibers of some families of spaces can help us prove representation stability theorems. So this is a kind of a slogan. And so I need still to prove that these are highly connected. And maybe this is not easier than just proving representation stability. But actually, in the case, so for example, in the case of configuration spaces, this property amounts to the following fact. We want to prove that the cubes, so the diagram that sends a finite subset of n to the configurations. So this will be, notice that the only map I can define here are maps that forget points in the configurations. So I have maybe to take the configurations labeled by the complement of S inside N, and you can see that if S is a subset of T, which is itself a subset of N, we will have a map from conf N minus S to conf N minus T. And so this gives a cubical diagram, so a diagram indexed by subset. And we need to compute the total fiber of this. Is it highly connected? And actually, this can be proved. This is already known, actually. Yes. You can see, for example, there's a book by Manton and Volich, which is called Cubical Homotopy Theory, where they prove so I'll state the theorem before going further. So the theorem is that this total fiber of this n cube for any manifold M, so closed, open, smooth, topological, this is n minus 1, d minus 2 connected. And the proof of this uses the generalized Blaker's-Massey theorem, which is exactly the kind of theorem that helps us computing the connectivities of total fibers of cubes. And this was, I think the generalized version was done by Goodwillie in one of the papers on Goodwillie calculus, V-calculus +3. So we saw that the cohomology, for example, we can deduce stability for both these invariants, hi of x, hi of configurations, or pi I. Actually, so first of all, it's not obvious that we can deduce that from an unstable information, because this stability for spaces is really for unstable homotopy types of configurations, and it's not obvious to see that the stability for the cohomology comes from something that holds already at the unstable level. So these two come from highly connectedness, and of this total fiber, which is so I want to say that this is an unstable information. Okay, so I have 4 minutes to add some kind of application also. So another application is for spaces of submanifolds. So instead of configurations, you could look at for a finite set S, fix a manifold P, smooth, of dimension P, and M, a smooth manifold of dimension M, let's say this is close, and this is arbitrary, so we can have boundary or not. And you can look at the space of something that I will call sub of p times n. Sorry, p times s into M. This will be the space of submanifolds of M, which are diffeomorphic to p times s. So it's really space of embedded copies of p, like this, inside M. And one can ask for, so if M is open, so if I have a boundary, there are, as always, stabilization maps, as in the case of contribution spaces. So if M open, you can stabilize and get maps like this. So a natural question is there homological stability? And also what happens if M is closed? And so one thing I can deduce with this kind of techniques is the following. So this will be more homological stability theorems than representation stability, but one can pass from one to each other with some arguments that I didn't explain here. And so the theorem is that if the Handel dimension of P, so no, let's forget about this. So if P is less than M minus 3 over 2 and M is open, then there is stability. And this reproves a theorem of Palmer from 2021. And it very, very slightly improves the range because his range was M minus 2 over 2. So again, half a dimension. And also if still with this range and M is closed, using representation stability techniques, you can show that there is instead stability over Q. So I need to restrain to Q to rational coefficients, and there's a periodicity phenomenon over FP. So this will mean that the homology of sub P times S inside M with coefficients in the FP will be the same if S is sufficiently big as that of sub of P times S plus big T M, and T is sometimes greater than 1. So this is a periodicity phenomenon. And this happens, for example, for conjugation spaces. But here we can show that it still holds for spaces of submanifolds. I think I'm done. I will stop there. Thank you.
Oh, I need to go teach, but thanks for the great talk.
Thank you.
Is there any question for the speakers? I'm going to stop the recording.